Have you ever, tried to fix a really complex problem only to realize that the way you were looking at the problem was actually the issue?
Oh, totally. It's a trap we fall into all the time.
Right. Like, imagine writing 1,000 lines of code. You have painstakingly anticipated, every single conceivable way a computer system could fail.
You've categorized them all.
Exactly. You've categorized them, you've named them, you've built this massive, impenetrable fortress of logic, and then at 2 a.m. on a Sunday, the entire system just comes crashing down.
And it's always Sunday at 2 a.m.
Always. And why? Because somewhere, in a completely different department, a programmer added a tiny typo to a single error message. That is it. A missing letter E, and your fortress just collapses.
It's painfully common, honestly. And not just in software either.
Yeah, totally.
I mean, we get so zoomed in on the hyper-specific details of the tools we use or the exact names of the obstacles in front of us that we build systems based entirely on rigid identities. And, well, rigid systems break.
They shatter. And that shift in perspective, moving away from asking, what exactly is this thing? And instead asking, what can this thing actually do? Well, that's exactly what we are exploring in today's deep dive.
It's such a subtle shift, but it changes everything.
It really does. We're going to look at how that one tiny shift in how you define a problem can completely transform the architecture of, well, really any complex system.
And our source material for this exploration is just fantastic. It's an excerpt from a tech blog titled The Secret Life of Go Error Handling Part 3.
Great title.
Yeah, it was written by Aaron Rose and published on tech-reader.blog. And it takes some very nuanced concepts from the Go programming language, which is basically the backbone of a massive amount of modern software.
Right.
And it frames them in a way that reveals a much deeper philosophy about problem solving in general.
Exactly. And I want to make our mission for this deep dive crystal clear right out of the gate for you listening. If you are sitting there wondering why you should care about a Go programming interface, just stay with us.
Yes, please do.
Because you absolutely do not need to be a programmer to grasp the core lesson here. We are going to uncover a masterclass in elegant system design that just happens to be, hidden within a specific coding interaction.
It's a very human story.
It is. To do that, Aaron Rose paints this wonderfully vivid scene. Picture this, right? We are in a classic Beaux Arts library in Lower Manhattan.
Oh, I love those spaces.
Me too. Think massive vaulted ceilings, dark polished wood, those little green glass lamps, and just the smell of old paper.
It's the kind of quiet, hallowed space where coding languages are debated as if they were ancient philosophy.
Exactly. A fitting setting for a discussion about the underlying elegance of logic. So, sitting at a heavy oak table in this library, we meet our two characters. First, we have Eleanor.
The seasoned veteran.
Right. She is a senior software engineer. She's been around the block, the one who kind of, sees the code like the Matrix.
I've worked with a few Eleanors. They're intimidating, but brilliant.
Totally. And sitting right across from her is Ethan, her junior colleague. And he is currently deep in the trenches, just looking completely defeated by his laptop screen.
And Ethan's dilemma is such a classic one. I mean, anyone who has ever tried to make two different computer systems talk to each other will feel his pain immediately.
Oh, 100%.
So Ethan is writing a background worker. For those unfamiliar, a background worker is basically an automated program that runs quietly behind the scenes, just doing chores.
Like a digital janitor.
Exactly. So Ethan's worker is supposed to sync data with an external API, which is another piece of software somewhere out on the internet. But there's a catch here.
There's always a catch.
Right. This external API is notoriously flaky.
Yeah.
Sometimes it answers perfectly. Sometimes it randomly drops the connection. Sometimes it just times out and goes completely silent.
It's the digital equivalent of trying to have an important phone conversation with someone who is driving through a mountain tunnel. You know the call is going to drop, so you just have to keep hitting redial. So to deal with this flakiness, Ethan has written a retry loop. Basically, if the data request fails, his code loops back and tries again.
Simple enough in theory.
It's simple in theory, right. But to actually implement this, Ethan has created what he himself calls a monster. It is this massive, unwieldy, towering if statement.
Yeah, and Eleanor, walking by with her cup of tea, takes one look over his shoulder at his screen and immediately identifies the architectural flaw.
She sees right through it.
She really does.
Yeah.
Ethan is exhausting a technique called an identity check. In Go, there is a built-in command called errors.is. It does exactly what it sounds like. It literally asks the system, is this error exactly 100% equal to this specific known error?
Okay, let's unpack this. Because Ethan is sitting there trying to anticipate every single specific network failure that could possibly exist in the universe.
It's a fool's errand.
It really is. He's writing code that says, if the error is an RTL's handshake timeout, retry. Okay, but if the error is a connection reset, retry. If the error is a DNS resolution failure, and on and on and on.
It's exhausting just to describe.
Right, think of it like a bouncer working the door at a very exclusive club. Ethan has handed this bouncer a guest list with 1,000 highly specific, complex names on it.
I love this analogy.
So every single time a person, or in this case, a digital error arrives at the door, the bouncer has to stop everything, pull out this massive list, and painstakingly scan through every single name to see if there is an exact letter-for-letter match.
And computationally, while computers process things incredibly fast, architecturally, this approach is a total nightmare.
Oh, completely.
Eleanor points out exactly why this is considered terrible design. She tells Ethan that he is creating a state of tight coupling.
Tight coupling, that sounds like a mechanical failure waiting to happen.
That's exactly how you should think about it. In system design, you want different parts of your system to be as independent as possible, like building with Lego bricks.
So you can pull one out without the whole thing collapsing.
Right, you can swap one out without breaking the whole structure. But Ethan's core business logic, the actual brain of his program that decides whether to retry syncing the data, is now permanently glued to the gritty, hyper-specific details of how the network operates.
Because he's hard-coding the exact names of those network errors right into his brain logic.
Precisely. If we apply it to a real-world scenario, imagine designing a car engine where, in order to change a single spark plug, you have to completely dismantle the entire transmission.
Oh, wow. That sounds awful.
It is. That is tight coupling, because the parts rely way too heavily on the specific internal details of each other. So Eleanor asks Ethan this devastating question.
What does she ask?
She says, what happens next month when we decide to swap out the HTTP client? Or what if the networking package you're relying on gets an update and the developers randomly add a brand new error type?
Ethan's response is just pure defeat, right? He just sighs because he knows he would have to come back into this specific file, open up his monster if statement, and manually add a 50th or 100th errors is checked to his giant chain.
Every single time.
Yeah. Every time the outside world changes even slightly, Ethan has to manually update his internal list. It is incredibly brittle.
And this leads to Eleanor's golden rule for system design. Identity checks asking, what exactly is this thing? They are fantastic for exact narrow matches.
Like finding a specific user ID.
Exactly.
Yeah.
If you query a database for a specific user ID and it isn't there, you get an error not found. That is a highly specific identity you want to check for. But for broad, messy, unpredictable categories like network blips.
Checking identity is just entirely the wrong tool for the job.
Entirely.
Right. So Eleanor tells him you shouldn't ask what the error is. You should ask what the error can do. And that right there is the pivot. That is the fundamental shift from identity to behavior.
It's profound.
It is. So how does she actually fix it? Because checking identity is clearly failing Ethan. So Eleanor introduces a solution called the behavioral interface.
What's fascinating here is the sheer elegance and simplicity of her solution. In Go, an interface is basically just a contract.
Okay.
It doesn't contain any actual operating logic itself. It simply declares a method that something else must have. So Eleanor deletes his monster code and types out a tiny one-method interface.
Just one.
Just one. It's just a few words long. She defines an interface that simply asks for a temporary Boolean method.
Okay, stop right there. Jargon alert. If I'm the learner here, I need to know, what exactly is a Boolean method? And earlier, the source mentioned errors being a struct. Let's translate this.
Fair point. Let's break it down. A struct is just short for structure. It's basically a custom container a programmer builds to hold data.
Like a box.
Right, like a box.
Yeah.
An error in Go is often just a struct holding a message. Now, a method is just an action that the container can perform. And Boolean simply means a true or false answer.
Oh.
So a temporary Boolean method is literally just a function attached to the error that answers true or false to one simple question. Are you temporary?
Okay, that makes perfect sense. But if I'm Ethan, I'm looking at Eleanor and thinking, great, you wrote a nice little true or false contract, but how does that actually help my giant list of 1,000 specific network errors?
It helps because of how Go handles interfaces under the hood. It uses a concept often referred to as implicit interfaces, or sometimes informally as duck typing.
Duck typing.
Yeah, meaning if it walks like a duck and quacks like a duck, the system considers it a duck.
Wait, hold on. What does implicit mean here? Do the network errors not have to sign a registry or explicitly declare that they are part of Eleanor's new contract?
No, and that is the absolute genius of the design. They don't have to explicitly declare anything to Ethan's code.
Really?
Really, all the developers of those outside network packages have to do is add a temporary method to their own error code that returns true. If they have that method, the Go compiler automatically recognizes that they fulfilled the contract of the interface.
Wow.
There is no central registry.
Yeah.
The compiler just checks the signatures.
Ah, I see. Okay, let's go back to our bouncer analogy to really nail this down. Under Ethan's old system, the bouncer was agonizing over a guest list of 1,000 specific names. It was a huge bottleneck.
That total nightmare for the bouncer.
Right. But under Eleanor's new system, the bouncer throws the guest list in the trash. Now, when an error walks up to the door, the bouncer just asks one simple question. Do you have a VIP pass?
Yes, exactly.
It fundamentally doesn't matter who you are. It doesn't matter if your name is RTL's handshake timeout or database connection lost. The bouncer does not care about your identity or where you came from.
They only care about behavior.
Right, what your pass allows you to do. Can you be retried? True or false? If true, come on in. The source material notes that these small, focused interfaces, things like checking if an error has a timeout method or a retry after duration, they act as standardized error contracts across entirely different, unconnected packages of code.
It is a profound shift in responsibility. Instead of the caller, Ethan's little background worker, having to know everything about every possible error in the universe, the errors themselves carry their own behavior.
That's so smart.
The caller just asks, do you conform to the behavior I need right now?
I love that. But Ethan, to his credit, is a good engineer, and he isn't totally sold yet. He immediately spots a potential flaw in this elegant plan.
Oh, he does.
Because if you know anything about modern software, you know that errors are rarely these simple, isolated things that arrive at the door one by one. They're usually tangled up in layers of context.
This raises an important question, and it's the exact hurdle Ethan points out. What happens when errors are wrapped?
Wrapped?
Yeah, imagine a network failure happens deep, deep down in the system's basement. The networking code wraps that raw error in a new message saying, failed to dial. Then the database code gets it and wraps that error in a message saying, query failed.
Oh, boy.
Then the application code wraps it again.
It's like a Russian nesting doll of failure.
Exactly. And Ethan looks at this and rightly says, okay, so the underlying root error might have a temporary VIP pass, but it is hidden deep inside 3 outer shells.
Yeah, how does a bouncer see the pass if it's buried?
That's his point. He asks, do I have to write a complex loop to manually unwrap this nesting doll, taking off layer after layer, and manually check every single one to see if it matches this new interface?
Because if he has to write all that unwrapping logic, Eleanor hasn't really saved him any work at all.
He's just traded a giant if statement for a giant unwrapping loop.
Okay, I'm with Ethan on this. If I have to manually dig through the layers, the elegance is completely ruined. But this is where Eleanor introduces the final piece of the puzzle.
The magic trick.
The magic trick. She tells him, no, you don't have to manually unwrap anything. She introduces a function built into Go called errors.as.
Which is brilliant.
Here's where it gets really interesting, because earlier we talked about errors.is, which checks for an exact, rigid identity match. Errors.as is completely different. Aaron Rose explains that errors.as doesn't just look for concrete identities. It actively hunts for behaviors.
That's the key distinction.
So Eleanor deletes Ethan's monstrous code and replaces it with just 3 lines using errors.as. But the syntax here gets a little deep. The source says you have to pass it a pointer to your interface variable. Can we demystify that? What is a pointer doing here?
Absolutely. The jargon can sound intimidating, but the concept is very straightforward. Think of a variable as a box that holds data.
Okay.
A pointer is exactly what it sounds like. It points to the physical memory address of that box. When you pass a pointer to errors.as, you are essentially handing out an empty box with a specific shape.
In this case, the shape of our temporary interface.
Exactly. And you're saying, here is exactly where I want you to put the answer if you find it.
Oh, I love that. It's like handing the system a blank form with your return address on it and saying, if you find anyone with a VIP pass, make a copy of it and mail it directly to this address.
That's a great way to visualize it. And the mechanics of how errors.as operates once you give it that pointer are just brilliant. It completely automates the unwrapping process.
It acts like an incredibly intelligent metal detector. You sweep errors.as over this Russian nesting doll of errors, and the language itself automatically traverses every single layer, from the giant outer doll all the way to the tiny root doll in the center.
Really by layer.
And at every single layer, it stops and asks, do you have a temporary method? Do you? Do you?
And here is the crucial mechanism. The moment it finds a layer that says, yes, I have that method, the metal detector doesn't just beep.
What does it do?
It physically extracts that specific layer's data, puts it into that empty box the pointer you provided, and returns true to Ethan's code.
It actually pulls the VIP pass out of the middle of the nesting doll and hands it to you.
It automates the extraction of behavior from complexity. Think about what that means for the resilience of the system.
It's massive.
It ensures that no matter how deeply buried an error is, no matter how many other completely unrelated packages have wrapped it in their own context, if the root cause adheres to that behavioral contract, if it can be retried, the system will recognize it and handle it gracefully.
And it does all of this completely behind the scenes. Ethan doesn't write a single line of logic to unwrap the dolls. He replaced a brittle, constantly breaking monster of code with just 3 lines of robust, intelligent logic.
Which brings us to the aftermath in our library scene. Ethan leans back in his heavy wooden chair, taking in the refactored code on his screen. You can just feel the realization of what just happened washing over him.
So what does this all mean? Let's zoom out and look at the big picture of what Eleanor and Ethan just accomplished, because the source material spells out the architectural triumph perfectly.
It really does.
Ethan's background worker program no longer needs to import the network package. It doesn't need to import the database package or the rate limiter package. It literally does not care who generated the error or what the error's official name is.
If we connect this to the bigger picture, Eleanor sums it up beautifully as decoupling at its finest. The producer of the error, say, the network router crashing, provides the context.
Right.
But the consumer of the error, Ethan's retry loop, only asserts for the behavior it cares about. Ethan has completely separated his logic from the messy realities of the outside world.
And this right here is exactly why this technical deep dive matters to you, the listener, even if you never write a single line of code in your life.
Oh, absolutely.
Because what we just walked through with Ethan is a masterclass in the evolution of problem solving. Think about the progression he made. At the very beginning of his career, he was probably checking error strings.
Oh yeah, literally writing code to see if the error message contained the word timeout.
Which is incredibly fragile because if a developer fixes a typo in the word timeout, the whole system breaks.
Then he evolved. He moved to checking identities. That was the giant if statement. Checking if the error was exactly the Airtails handshake timeout struct.
It's better than checking for a typo, but as we thought, it's still a massive liability when you are dealing with broad, unpredictable categories of failure.
From there, he might have tried checking raw data structures, but ultimately he arrived at the pinnacle of system design asserting behaviors.
Right.
Decoupling is truly a superpower. It transforms an application from a tangled, fragile mess of dependencies, where pulling one single string unravels the whole sweater into a flexible, resilient architecture.
That's a great way to put it.
By shifting from identity to behavior, Ethan's error handling went from being his biggest liability, the exact thing that was going to wake him up at 2 a.m. when the code broke, to being a structural strength.
It's incredibly satisfying when a concept clicks into place like that. So let's briefly recap the core takeaways from Aaron Rez's deep dive before we wrap up.
Sounds good.
Remember the golden rules of architecture here. Identity checks using tools like errors.is are for narrow, highly specific matches. It is a lock and a key. If you need exactly one thing, check its identity.
Behavior checks, on the other hand, using interfaces, are for broad, messy categories. You throw away the guest list and just ask, can you do this action?
Yeah.
Rather than, exactly who are you?
Exactly. And finally, when dealing with complex, layered systems, tools like act as your magic metal detector, automatically traversing the Russian nesting doll of complexity to find and extract those behaviors for you.
It is a highly effective, incredibly elegant way to manage chaos in a digital environment.
It really is. And it leaves me with a final thought that I want to pass on to you. Mull over on your own time. We've spent this entire deep dive seeing how software systems become drastically more resilient, adaptable, and elegant by focusing on behavior.
What something can do.
Right, rather than rigid identities exactly who or what something is. So how might this exact philosophy apply to human systems?
Oh, that's a fascinating question.
Think about the organizations you work in, the teams you build, or even your personal life. How often do we create brittle architecture in our own lives by obsessing over rigid identities?
We do it all the time. We hire based on highly specific, rigid job titles or exact academic credentials.
We define people by fixed labels. We hand the bouncers of our organizations a guest list with 1,000 exact requirements, and then we are shocked when the system bottlenecks or breaks when the outside world changes.
We need more interfaces in real life.
We really do. What would happen if we stopped asking what exact identity does this person or this situation have, and instead started designing systems that simply ask, what behaviors do we actually need to move forward?
It's a powerful shift in perspective.
Maybe the key to fixing our own complex problems isn't obsessing over the exact brand of the wrench, but simply recognizing what the wrench is meant to do.